Professor Mehran Sahami, what an honor to have you here. This is awesome.
Thanks so much for having me. It's great to be here.
I, as the person who got me into computer science and began a journey that changed my life forever, I really can't express how much it means for you to be willing to have this conversation with me and chat about some of the stuff that happened along the way. Um,
That's so kind of you. Well, I'm glad after you took a class with me, you stayed in computer science and didn't run away.
well, I actually it's interesting because I wanted to frame this conversation around the topic of chances, and I took 106A, got the basics of programming, and I thought, wow, this is it. This is what I could do. And then I also took 109 with you, and I was like, I am mathematically unprepared for some of the sophistication that we dealt with. But since, with a bit more distance, I think I've reappraised my interest in probability. And I sort of would love the chance to discuss some of these topics with you because now I'm sort of drawn to it intellectually as this magical thing that empowers decision making. Um, and I didn't see it like that at the time. It was a class that I needed to pass. And so I wanted to ask you first and foremost, what got you into probability?
That's a good question. I mean, I think growing up, I was always kind of interested in math kind of things, but it was really once I got into school and had a chance to formally kind of learn more about probability, it just seemed fascinating. And then in graduate school, I was working on machine learning stuff. I like to say before
Mhm.
machine learning was cool because this would have been, the mid '90s. And one of the big formalisms for being able to come up with new algorithms and new methods was probability theory. So that's what really got me into probability. And while I was in grad school, I also took some classes on decision analysis that were in departments outside computer science, and just saw the way that probability could be used not only as a way to analyze data or to build models,
Mhm.
but also as a way to kind of think about decision making processes, and is really just a formal way of getting more clarity of thought around taking next steps. That just, when you
Mhm.
actually see mathematics turn into something that affects action in the world, that got me really excited.
And it's also, I think it's really interesting. I think having some experience now, I know that you were also an incredible proponent of making it a core part of the computer science curriculum. That you were a huge advocate for having computer scientists reason around these things. And I've come across some stories over time of people not taking into account probability and then paying the price for it. Um, and I would love to get into some of those later. But some of incredible stories from Pixar and other bugs that are just like haunting in my dreams. Um, and okay, but so let's talk about probability because it's I've always thought about math as like a computational tool to derive truth from what we know. But all of a sudden, with probability, we're talking about deriving truth or knowledge from what we don't know, or at least working with imperfect information. So why don't we start at the very beginning and say, what is probability?
Sure. So probability at the most basic level, sort of an intuitive understanding, is the chance that something will happen, right?
Hmm.
But one of the things I think people find fascinating about probability is, we put all this mathematics around it. At its fundamental core, what a probability means is actually something that there isn't universal agreement on. There's different views of
Mm.
what that number actually represents. There's one view called the frequentist, which basically say what a probability is, it's basically sort of the long run chance of something happening. So let's say you have some like coin and you want to know what its probability is of coming up heads. You just keep flipping that coin over and over and you see what fraction of the time it comes up heads. And if you
Mm.
want to be sort of more precise mathematically, if you were to flip the coin infinitely many times or as you go to infinity, that fraction of times that it comes up heads is the probability of heads, right? That's the reason why it's called frequentist, is basically you're just looking at frequencies of things happening. There's another school of probability called Bayesian probability. And what Bayesian probability looks at is it looks at probability as your belief of something happening. So it's not about the notion that I just do something multiple times, but it's there. What that chance actually represents is what do you believe is the likelihood of something happening. And so to contrast them a little bit, I can ask you, like, what do you think is the probability of it being sunny tomorrow where you're at,
Mm.
right? And you could say, oh, well, you look outside, look at what it's the temperature is like, what that's kind of been in the past. You say, I think there's an 80% chance it'll be sunny. It's like, what does that mean? Is that your belief that it's going to be sunny, or have you actually observed tomorrow infinitely often, and 80% of those tomorrows were sunny? And so people will say things like, well, but you look at that same day on the calendar and years back, and you look at a bunch of other things. Like, okay, you're bringing all this other knowledge to bear, but you're not actually measuring the frequency of that particular event. And so
Hmm.
that's why philosophically, and people have these different views.
Hmm.
Now, mathematically, a lot of similar mathematics gets used for both of these things. But
Hmm.
it's this interesting philosophical question that that number actually means something different.
Well, it's I think doubly fascinating because I think me in particular, I think I fell into the Bayesian bucket very quickly. Like you're trying to um, find a mapping from a subjective belief state in and narrow it into 0 or 1, or the numbers between 0 and 1. um, and I guess I never even thought about philosophically requiring infinity to believe in something, when you probably will never have even you're never going to actually compute something infinity times, right? um, and so it's really interesting that I think Bayesian also has this humility approach that says, like, given the best information we have, this is our belief that this is going to happen, as opposed to some sort of metaphysical declaration about what the true state of affairs in the world, if you had access to infinity, is. Whoa, that was a mind fuck. Um, okay, so the chances that something will happen, and I think the basic, the coin toss is the perfect example. Rolling the dice is another perfect example. Um, I think of it as, like, there's a surface area of possibility, and you want to find, where in that surface area are you going to land. And that, I think, that was one of my first roadblocks in CS 109, was the combinatorics of it, and just reasoning around how different possibilities can combine to make more possibilities, that give you the result of that space, right? So how do you think about combinatorics? I mean, the relationship between combinatorics and probability, such that it gives the foundation with set theory to then start building this intellectual, edifice.
Yeah, I mean, I think it's one of the ways that's a way to move into the realm of probability. Like in terms of teaching it, one of the things we often do is we talk about probabilities for things that are equally likely, right? So if you roll a
Mm,
die and the die is fair, so all the sides could come up with the same chance, then it's equally likely. And now you could do something like, say, instead of one die, and die is the for folks who are listening, the singular form of dice, rather than having one, let's say you had five dice, right? So
mhm,
now when you want to think about rolling five dice, there's lots of different combinations you can get, right? It's six to the fifth
mhm,
power because you have five dice. There's
mhm,
six combinations for each of the die. So you have to think about what are all the different ways, for example, on those five dice, you could roll, like, say, the number 25. Right.
mhm,
So there's a lot of different ways you can do it. And so the combinatorics are basically trying to understand, for things that are equally likely, I have some fraction of the number of events that satisfy the condition I care about, like all
mhm,
the possible ways I can, on five dice, I can roll a 25, divided by how many different ways the dice can come up. And
mhm,
so it's basically just counting, right? You count all the possibilities, but it's a way to begin to think about probabilities as a moving from the world of counting, which people kind of have some more basic
mhm,
familiarity with, into the world of how does that translate into a probability. And then from there, we can take another step and say, well, what if the dice is not fair, right? What if the sides
mhm,
come up with different things with different probabilities? And then we move into the realm of things that are not equally likely. And so
mhm,
we bring, rather than just counting, we bring some other machinery to bear in terms of doing the computation.
mhm. And what are some other approaches? So counting is, the one that we took. Do you know of other approaches to ease people into these concepts?
Well, so, one of the things you can do is, rather than kind of taking the combinatorial approach, you can kind of take an approach that starts with a grounding of thinking about, probabilities of the chance of something happening. You can actually start really with
Mhm,
the Bayesian approach
mhm,
and say, okay, if probability is your belief, then we need to think about a couple different things. We need to think about what information that you may have observed about the world that you're going to
mhm,
incorporate into your probability. And then what prior belief did you have? And so we start
mhm,
from the standpoint of, like, what did you already believe? What's the new information you get? And how does that update to some
Hmm.
new probability, right? Or conditional probabilities we talk about. So you start at a place of thinking about the notion of prior and posterior probabilities
Hmm.
from kind of the Bayesian aspect, rather than kind of thinking about these counting kind of arguments, which they don't have to. You don't have to think of it as frequentist in nature, but it sort of moves
Hmm.
you more in that direction.
And I think this is also something that is very intuitive for most people. You meet somebody new, and you're informing your approach to that person as the aggregate of everybody you've ever met for the first time. And as soon as you get more information, you start calibrating how you talk to them. Say somebody's in a grumpy mood, you wouldn't expect somebody necessarily to be in a grumpy mood, but within a few interactions, you could probably pick that up and calibrate your message to be more effective that way. Um, there's also something really cool when we get to conditional probabilities and Bayes' rule, and I think reasoning around co-occurrences that I think is beyond cool, which is when we try and map operations like or and to the subset between 0 and 1, and that we find ourselves with these intuitive operations that if you are calculating the possibility of a and B, that is multiplying the probability of the two. But if you're computing or thinking about the probability of A or B, you're thinking about the addition. And I wanted to riff off of that with you because, like, how do we get from something that exists in what I feel like is a very subjective world to something so concrete as like the order of operations in math that we use to compute these values?
Yeah, and I think what you're hitting on is one of the, I think, most crucial concepts in probability, which is the concept of independence, right? So
Mm-hmm.
what I care about is, like, there's these two things that could be happening. How related are they to each other? Like, if the first thing were to happen, does that give me any information about the second thing happening? Right. And so a way to think about this, and sometimes you get some counterintuitive results, is like rolling two dice. So let's say I have two six-sided
Mm-hmm.
dice and they're fair and I roll them. And I say, I want to figure out what's the probability, say, of rolling a 10. Right. And so if I don't give you any information, you'd say, well, a 10, there's, three different ways that can come up. I can roll a 6 and a 4, a 5 and a 5, or a 4 and a 6 out of 36 combinations. So it's 1/12. You're like, okay, that can do the combinatorics. And I say, okay, what's the probability of a 10 coming up if I tell you I rolled a 5 on the first die? So now I've
Mm-hmm.
given you some information. And you realize that that sum of 10 is dependent on what I rolled on the first die, right? So now if I
Mm-hmm.
told you I rolled a 5 on the first die, it's no longer a 1/12th probability. It's a 1/6th probability, because now the
Mm-hmm.
only thing that remains is, if I roll a 5 on the first die,
Mm-hmm.
if I roll a 5 on the second die, that's what I don't know. And
Mm-hmm.
similarly, if I told you I rolled a 1 on the first die, what's the probability of getting 10? You immediately know it's 0, because it's not possible, right?
Mm-hmm.
The place that this becomes counterintuitive, though, is when mathematics and me, this is what I tell my students: when mathematics meets intuition, guess what wins? Math, right?
Uh-huh.
So if the sum is 7, if I say I have two dice, and what's the probability I roll a 7? And now I'm going to tell you what the first roll is. Does that
Hmm.
actually affect what the probabilities of rolling a 7? And you would think, well, yeah,
Mm.
10, it made a difference. There was a dependency there. It turns out for the sum of 7, it's the only sum that this is true for two dice. It's independent of the first roll. And you're like,
Hmm.
why would that be? Right? And the reason why is, think about it. No matter what you roll on the first roll, there is exactly one value on the second die that would make the sum 7. Right? So if I roll a 1 on,
Hmm.
I have to get a 6. If I roll a 2 on the first die, I have to get a 5. And so what I get on the second die for it to match with the first die to get a sum of 7 is always 1/6. So mathematically, if the sum is 7, knowing the value of the first die doesn't change your probability for getting the sum of 7. So these things actually become independent. And so showing examples
Hmm.
like that to students helps them separate the intuition that says, well, if I have a sum,
Hmm.
it's always the roll. First roll is, always the sum is always going to be dependent on what I get from that second roll. It's like, no, it turns out there's actually some sums, in this case, seven's the only one, for which that's not true. And
Hmm.
beginning to tease those things apart allows students to see the difference between, okay, what do I intuitively think about this versus what the dynamics of the problem really are.
Hmm. What you said also reminded me of a really funny line that you had, which wasn't about math and intuition, but a similar opposition between theory and practice. And I think it went something like, when theory and practice meet, like theory practice brutally brutally mauls theory, or something like that. Theory takes a while to recover after being brutally mauled by practice. um, um, and no, but there are some very unintuitive notions in probability that sort of emerge as you engage with these topics more deeply. You are also reminding me of the Monty Hall problem, the very famous case. You want to lay it out for somebody who's listening?
Sure. So the Monty Hall problem comes from the TV show Let's Make a Deal that had the host Monty Hall many years ago. And basically, the setup for the problem is you have three different doors. Behind one of the doors is a prize, and the other two doors are empty. Or in the TV show, they were goats, but I don't think you actually got the goat. Um, and so the host lets you pick one of the doors. So you pick one of the doors, and it's equally likely that the prize is behind each of the three doors. So you pick one of the doors, and then what the host does is opens one of the other doors to reveal, and they're guaranteed to reveal a door that's empty. Okay.
Hmm.
And then they say, would you like to switch to the other remaining door? And the question is, should you? Right now, when I was a kid, I'm actually old enough that I used to watch Let's Make a Deal with Monty Hall. And when I was a kid and I didn't understand probability, I would always sit there and say, "Don't switch, don't switch. He's trying to fool you," right? Because I didn't do the math. and and I was a suspicious kid, right? So that's just the backstory.
Healthy skepticism.
That's all you know. In science, you should always have healthy skepticism. Um, but you do the math, and it turns out that you should actually switch, right?
Hmm.
Because when you pick the first door to begin with, your chance of picking the right door was one third, right? Because you're just picking
Hmm.
essentially randomly among three doors, and it's equally likely the prize is behind either one. But if you think about the different cases, there's a one third chance you pick the right door. And if you pick the
Hmm.
right door, after the host opens up one of the other doors, if you switch, you're switching away from the right door. So you're
Hmm.
going to lose. Okay. But there's a two-thirds chance you picked the wrong door, right? When you picked your first door,
Hmm.
right? There's only a one-third
Yeah.
chance you would win. So there's a two-thirds chance you picked the wrong door. So if you pick the wrong door, right? So you picked a door that's empty. There's two other doors left. One of them has the prize, the other one doesn't. The host is forced to open the door that doesn't have the prize. So
Mm.
that's where the dynamics of the problem actually
Mm.
force information. You're getting information about the
Mm.
problem because the host is forced to make a particular decision in that case, which means of the remaining two doors, you don't have the prize behind the one that you've selected. The other one is guaranteed to have the prize behind it because the host couldn't open that door. So if you switch,
Mm.
you're switching to win the prize. So now you have to back up and you have to say, okay, so if I initially picked the door that had the prize, that was a one third chance. And I
Mm.
switch, I lose. So one third of the time, if you switch, you would lose. But two-thirds of the time, I pick the wrong door. And if I switch,
Mm.
I'm guaranteed to switch to the winning door. So doing the switch actually has a two-thirds chance of leading to a win. So
Mm.
it seems very counterintuitive. And sometimes people think, well, maybe it's only a 50% chance because there's only two doors left. No, because when you first made your choice, there were three doors, and there was a two-thirds chance you picked the wrong door. But
Mm.
if you switch in that case, you are switching to the winner. So there's still a two-thirds chance you will switch to the winner.
Mhm. It's crazy. I mean, like it is, and it's such a good exercise for thinking about changing, I guess, priors, right? Like you're updating your model to incorporate the latest information, and you have to. I don't know. It's such a humiliating is the wrong word, but like humbling maybe, where you have to accept that the world that you were operating under a turn before existed in a different axiomatic space than the world that you operate in now, even though we're talking about the same choices, which I think is just helpful for anybody to think about and to really sit with it. Because it really, like, as the Oracle in the Matrix says, it really bakes your noodle. Um, and and I think it also, this might be a great segue to talk about expected value. Even the way that you were framing the problem, like you were already quantizing it into like there's one third chance that I'm gonna get something, there's two-third chances that I'm gonna get nothing, and sort of trying to understand what the expected outcome of a given situation is given the probabilities around it. So why don't we talk about expectation a little?
Sure. I love expectation. It's a great
I know
topic.
you do. I know you do. I know you love the linearity of expectation. I hope
Oh,
to get
there's
to
many things about, yeah, that's one of the big ones. But like,
it.
expectation is basically just a fancy way of saying average. It's a weighted average,
Mm,
right? It basically says if I look at all the possibilities that are going to happen and I weight them by the probability of them happening, right? So I basically take the probability of something happening multiplied by essentially the value of that particular thing. And I sum over all the possibilities, that's the expectation. Basically a weighted average, weighted by the probability of something happening. And the thing that I really like about, well, one of many things I really like about expectation is you can use it to think about real world decisions. So there's this notion of what's referred to as maximizing expected utility, right? So I have
mm-hmm,
some decision I need to make based on that decision. There's potential outcomes that can happen based on each decision. And there could be uncertainty, right? So I make a decision,
mm-hmm,
and then there could be 3 or 4 different things that could happen after I make that decision. Each one has some probability associated with it, but I don't know which one's going to happen. So I can
mm-hmm,
say, well, what do I, if I make that decision, kind of what's the overall value? If I were to take the weighted average over all the things that could happen, can I give some value to that decision? And that's kind of where you get into decision analysis. And
mm-hmm,
when you think about all the possibilities, if you think about the different terms, maximizing expected utility, the expected part is computing the expectation, computing this weighted
mm-hmm,
average. The utility is how much value you get from each of the possible outcomes that could have happened. And the maximizing basically says, well, let's say you need to make one of 2 decisions. You make the one that maximizes or has higher average weighted value over all the things that can happen, right?
mm-hmm,
So, like, one of the examples we did in class was buying a lottery ticket. So you could buy a
mm-hmm,
lottery ticket for $1, and you could say, let's say you win the lottery, you win $1 million,
mm-hmm,
but the chance of winning the lottery is say 1 in 10 million, right? So you could
mm-hmm,
say, so what's the expected value of buying the lottery ticket? Well, if I buy the lottery ticket, I have to spend $1. And
mm-hmm,
there's 2 possible things that can happen if I buy the lottery ticket. One is I win the lottery and I get $1 million, or I lose the lottery and I get nothing. And I've already paid the $1, right? So I have a
mm-hmm,
-1 to begin with. Well, what's the chance of winning the lottery? It's 1 in 10 million. What's the payoff there? It's $1 million. So in that case, the expected value, the average, is basically 1/10, right?
mm-hmm,
Because the if I get 0 from the lottery, I'm getting nothing, and there's basically a 1 in 10 million chance I get $1 million. So I multiply those things
mm-hmm,
together, I get 1/10. So the value of the lottery ticket in that case is -1 for buying the lottery ticket plus 1/10. So basically it turns into -0.9, or you could think of as -90 cents.
mm-hmm.
What happens if I don't buy the ticket? Well, if I don't buy the ticket, I'm guaranteed to not win the lottery. Okay. So
Fair,
my
yeah.
probability of not winning is 1, or my probability of winning alternatively is 0. And so my payoff is 0. And so now I make the
Mm,
choice to maximize. They say, well, over here, buying the ticket gets me -90 cents. Over here, not buying the ticket gets me 0. What am I better off doing? And you say,
mm-hmm,
well, don't buy the ticket, right?
mm-hmm,
But it turns out, so people often say, like, you just shouldn't buy lottery tickets. Well, it turns out if the lottery paid $1 million and your chance of winning the lottery was 1 in 100,000, you should probably actually buy the lottery ticket. That just almost never happens in the real world, right? So I'm not saying people should buy lottery tickets, but it's just, it depends on how you compute those, thinking about the probabilities and what the payoffs are.
mm-hmm. And this reminded me a little bit of something we touched on in class too, which was the double or nothing strategy. And how you can sort of, that is also counterintuitive result where you're sort of like, okay, you want to talk about that a little bit to
Yeah, there's this famous problem. It's called the St. Petersburg Paradox. I'm not sure why it's called the St. Petersburg Paradox, um, but it is. And basically, what it says is imagine you're making kind of even money bets. So, like, you're
mm,
betting on something, and if you bet $1, and if you win, you get an additional dollar back. And if you lose your dollar. And there's a betting strategy that says every time you lose, you double your bet from the time before until your next win. So let's say I bet $1 and I lose. Next time I bet $2 and I lose. Next time I bet $4 and I lose. I bet $8. Now, if I win, I go back to betting $1. And
mm,
the interesting thing about this, because you're doing the doubling, is as soon as you win, that win covers all of your losses from before in this kind of round
mm,
of sets of losing, plus an additional dollar. right? So if you look at the case we looked at,
Mm.
let's say you lose $1, then you lose two more, so you're up to $3 lost. Then
Mhm.
you lose four more, so now you're up to what? Let me get the fingers right. You're up to
7.
$7, right? And now you win $8. So what happens? You make back all of your
Mm.
loss and you gain $1. So you keep losing until you get a win. And when you get a win, that entire series of
Mm.
things basically you come out $1 ahead. And if you're like, well, $1 isn't very much, multiply it by 1,000, multiply it by a million. You
Mhm.
can multiply it by whatever you want to make the dollar values really big. And so you see that betting strategy and you're like, wow, I can't lose. Well, the problem is sometimes you don't stop at 8, right? You lose at 8 and you lose at 16,
Mm.
you lose at 32 and you keep going. And because this thing is growing exponentially because it's growing by powers of 2, you can hit a point where you can't make the next bet because you've run out of money, right?
Mhm.
Or if you go to a place like Las Vegas, they prevent you from doing this by having like betting limits. Sometimes people wonder like
Mm.
Las Vegas, they want you to gamble. Why would they have betting limits? It's precisely so you can't do this kind of stuff.
Mhm.
But if you
And
could,
because go for it.
go
Sorry,
ahead.
go for it.
No, I was going to say, like, if you had infinite money and you could make infinite bets, this actually says basically your expectation for each round of betting is always positive. So you should just keep
Mm.
doing it. The problem is we don't have infinite money and we can't make infinite bets.
Right? Or if we had infinite money, we wouldn't be worrying about this stuff anyway.
Yeah, exactly. Like, why do you want $1? Like, you got infinite money.
I was also going to add like margin calls and margin limits in trading scenarios where there are situations where a brokerage will lend you money to trade, assuming that know what you're doing. This could be very powerful, but if you don't know what you're doing, this could be terrible. And those have limits too. So there's very much the same idea of institutionally you need a cap because nobody is equipped to deal with infinity. I think it just echoes back
Yeah.
to the idea of frequentism. So what other stuff about expectation can we chat about? There's linearity. Are there other things that you particularly like about it?
Yeah, I think one of the things about expectation that is also pretty neat is that when you think about intuitively, what does it sort of mean, right? Because you can think about, like in this case with the St. Petersburg Paradox, like when you average over a bunch of things, there could be some things with very low probability, but that have very high payoff that can skew what you do. And so then it becomes really important to be precise about what your probabilities really are. And
Mm,
it gets into a notion of it gets into interesting psychological phenomena. So one of the things also
mm,
about, there's normative decision making, which is you kind of bring all this machinery from decision analysis and probability theory and utility, and you put it all together in terms of trying to make decisions. And then there's descriptive decision making, which a lot of psychologists have looked at, including like Amos Tversky and Daniel Kahneman, who
mm,
did a
mhm,
series of well-known studies. And Kahneman won the Nobel Prize in economics a few years back. Um, and Tversky certainly would have won it with him if he was still alive, but they don't give
mhm,
the Nobel post posthumously is the word I'm looking for.
mhm,
Um, but the idea there is that people have a real tendency to prefer certainty, right? So
mm,
when we look at something which is like a 99% chance of something happening versus a 100% chance of something happening, we view that 1% differently than if we looked at something that was like a 50% chance of happening versus a 51% chance of happening. Like both of those
mm,
still have a 1% difference, but when that 1% is at the point of certainty versus uncertainty, we just treat it differently. And that has
mm.
to do with our psychology, right? The math can, you can work out the math and be like, well, you should treat these situations the same. It's 1% difference. But people just deal with it differently. And so that speaks a little bit to, when we want to do some computation around expectation, we need to think about not just the mathematics, but if you're making real world decisions, how that
Mm.
mathematics actually meshes with someone's psychology to make the decision.
There's also a fascinating point that is like, even thinking about my life or thinking about the world in general, is there anything that has probability one?
It's a good question.
Mm,
I'll give you an example that I always thought was fantastic because Ron Howard, who's considered the father of decision analysis, taught this class at Stanford on decision analysis that I took, and I just thought it was brilliant. So and that was
mm,
part of the reason why I work some of that material into other classes I teach. But the way he would give exams in the class is they were multiple choice exams, but rather than picking the right answer, what you would do is assign probabilities to the four possibilities, right? Because he wanted you to think about this. And then it was graded on a logarithmic scale, right? So just thinking about how to take the exam forced you to think about probability. But if you think about what that means, it means if you give the correct answer zero probability, your result from that one question by itself is negative infinity because you're taking the
Hmm.
log of zero, right? Which means you
Hmm.
immediately fail the class. That's unrecoverable, right? On one question, on any exam, if you give zero probability to the right answer, it's game over. You have failed the class because your
Hmm.
score is now negative infinity. You can't recover from that. So it forced, and the reason why he did that wasn't he wasn't trying to be mean. It forced you to think about I got to be really, really sure to give zero probability something, right? And so when I was taking the exam, like I wouldn't give, like even when I was like, I know that's not the right answer, I wouldn't give it a zero. I'd give it like a 0.0001, right? Something like
Hmm.
that. It's like if something happened, like if some cosmic ray hit my brain and I misread the question or something like that, um, I still wouldn't fail the class. I mean, I might get a big negative score, but hopefully that might be recoverable.
Hmm.
And it just made you think about that, like how few things there are in the world that have absolute certainty, right? Because there's
Hmm.
always these tiny shit, like a meteor can hit the planet and it's game over. So we're like, well, I'm
Hmm.
really sure this thing's going to happen. It's like, well, do you have control over everything? There's all these things in the world that have very small chances of happening that we just tend to discount because it would be just
Hmm.
way too much complexity for our mind to try to deal with them all at once. Like, what do I want for dinner? Do I need to take the possibility of an asteroid collision like into that question? It's like, no, you just can't do it. But what it brings up is the notion of like there's a lot of things where we just accept as certainty, even
Hmm.
though they're not a probability one event in some sense, but they're so
Hmm.
close to it that in terms of daily decision making, we just accept it that way.
Hmm. And this reminds me of Laplace smoothing, where thinking about the probability that the sun will rise tomorrow. Um, I've always seen the sun rise. Every day I see the sun rise, but you have to sort of weigh the fact that things may change tomorrow. And I know I think of Laplace smoothing as being like the perennial hack. There's a bug somewhere in the system, and you're like, what? When? Just add a one. Like it can't be zero, so just add a one. Um,
No, it's a
what
great
other?
point.
No.
I think like one of the things, right? Like the one of the ways we motivated in class, for example, is imagine you have a coin that you want to flip, and you want to figure out what's the chance it comes up heads, but you've never flipped it before, right? So you have
Hmm.
no idea what its probability really is, but you might look at it and say, yeah, this a quarter that looks kind of like other quarters I've seen, so I think there's a pretty good chance that it's going to come up 50-50. I don't know
Hmm.
that because I've never flipped it before. I've never observed it, but I think there's a good chance of that. So you have some prior probability, and depending on how strongly you believe that this thing is close to 50-50, that's your prior. And so Laplace gives you a way of saying, I'm going to have a very simple prior. Basically, I'm just going to pretend I saw one head and one tail in the past, which still makes the most likely probability 50-50 because I've seen one of each. But if I start flipping this thing and I keep getting heads, 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 when I incorporate that information in, my probability of thinking that the coin can actually come up tails is very rapidly going to go to
Hmm.
zero. It won't become zero exactly, because then again, things might become
Hmm.
problematic, but it will become very close to zero. Because it is, in fact, possible to take a real coin that's 50-50 and flip it 20 times and have it come up heads every time.
Hmm.
That doesn't mean you're guaranteed that the coin is always going to come up heads. It just means you encountered a very unlikely scenario, but you still want to have some possibility that tails could come up in the future.
Hmm. Um, and so this is making me think. You mentioned things being graded on a log scale, and then the value of expectation for making decisions. A lot of this stuff that you were mentioning happens at a very very low probability states, right? Like 0,0000, something really tiny. And in order for us to even, I mean, as humans, to be able to reason around them or deploy systems that reason around them, the hack that we've found is to convert that to logarithmic scale, right? So that we can more easily compute with, you're talking about the degree of the power that is sort of affecting the result way more than the actual, like three at the 10th significant digit. Um, how does that innovation occur? I don't think I ever registered where that came from.
Yeah, I mean, one of the things, in probability is like, what operations you use. And for things like we talked about in independence before, when you have
Mm,
two things that are independent and you want to say what's the probability of like both of them happening, when they're independent, you just multiply them together. Right.
mhm,
And so we could think like in a machine learning context, like in a context where people are doing a bunch of data analysis, one of the things that's often assumed is that each one of the data points that you're seeing is independent and what they refer to as
mhm,
IID, independent and identically distributed. But what it means is if I see three different data points and I want to say what's the probability of seeing these three data points, it's the probability of seeing the first multiplied by the probability of the second multiplied by the probability of the third. And so doing a bunch of multiplications, especially with very small values in a computer when we're using floating point, right, those values can oftentimes go very close to zero. We can get problems with like underflow or stuff like that. What log gives us is it gives us this neat little hack that says if you take two quantities and you're going to multiply them, if you take the logarithm of that, it's equivalent to adding them in the log space. And
mhm,
adding is a much more efficient process on most modern
mhm,
computers, and also doesn't run as much into this underflow issue because when we're not multiplying a bunch of small values that are getting us equal to zero, we're just adding some things, and some of the values might be negative values, which would correspond to a very low probability, but usually we're not going to underflow when we're just adding stuff together. And the
mhm,
nice thing about this is that log is what's referred to as a monotone transform. And what that means is if I'm thinking about maximizing some probability by multiplying a bunch of stuff together, the the particular thing that will maximize that quantity is the same thing that I will get by
mhm,
maximizing the log of that quantity,
mhm,
right? And so when we do these things like, oh, I want to compute the most probable thing to happen here, that means I want to find the thing with maximal probability. That's actually exactly equivalent to finding the thing with maximal log probability.
mhm,
So it's a thing that mathematically is easier to compute, is more stable, and generally gives us the same result as kind of doing all the multiplications. It
mhm.
just makes the math easier, basically.
Yeah, but and it's a I think it's also one of the clearest examples I could think of mathematics really, giving engineering a 10x advantage, if not more. Where sort of, you're trying to refactor your problem. You wrote code to solve a problem, and you're trying to figure out what the next improvement could be. And you use mathematics to redefine the problem space, and you trust in the, sacrosanct sanctity of mathematics to make sure that when you re-implement your code, and instead of checking for the probability, you check for the log probability, that that's going to give you the same result. um, no, it's so cool, and I think this is adjacent to practical computing and pragmatics of the linearity of expectation. um, and
Yeah.
I mean, it's funny because like it's almost 10 years since I took the class, but I remember so distinctly how excited you were about expectation being linear. So it would be awesome to unpack that a little.
Well, it makes a lot of computations about things easier. And one of the things that's kind of neat about linearity of expectation, too, is a lot of times you can think about you define a whole bunch of separate variables. And what you want is kind of the expectation of some aggregate thing happening. If you can
Mhm,
define that aggregate thing in terms of a bunch of separate variables, you can
mhm,
compute the expectation of each one and add them all together. And the neat
mhm,
thing about that is that works even if the variables are dependent on each other, which oftentimes they can be when you sort of dissect it that way. But it just becomes a really powerful tool for computation is to say, wow, there's the thing I care about, the expectation of actually is this big complicated thing. If there's a way that I can reduce it to a bunch of separate variables where I can think like, well, what's
mhm,
the chance this is true? What's the chance this is true? What's the chance this is true? And in total, they represent this thing that I care about. Mathematically, it just kind of works out. And so that was one of the things, we didn't. I'm trying to think if I can remember a particular problem from class, but it's been a while since the
mhm,
last time I taught 109.
mhm,
But it's just the same way that we think about like programming, like breaking it, like problem decomposition. I want to write a big
mhm,
program. I'm going to break it up into a bunch of functions, and that helps me manage the complexity. I almost think about the mentality for linearity of expectation being used the same way. It's like, here's this complex thing I want to compute. I can actually break it down as a bunch of small things and then add them together.
And it also reminded me of some of the other interesting stuff when you get deep into the math of probability, that you start seeing these other, celebrities in math show up in places that you don't expect. You see pi show up in places that you weren't expecting. You see, sigmoid functions. You see, all these types of things that you wouldn't necessarily be able to intuitively say that this belongs here, but that like computationally very difficult to do. Even like the z tables. Like you use a lookup table to figure out what the right outcome is because they're so complicated to compute. But it's just so interesting, and philosophically, the pursuit of uncertainty of truth through uncertainty is just fascinating to me.
Yeah. I mean, like,
I like
one
there.
thing along those lines is like the central limit theorem, right? Which I just
That
think
was
is this.
literally the next question. That
Oh,
was
really?
literally
Really?
yeah. Here, let's go for it. Yeah.
All right. I mean, it's a thing of beauty. It's kind of astounding, right? That when,
Yeah.
like, I mean, the mathematics kind of play out, but then you actually see it like in the real world. You're like, why is
Mm,
there so much stuff that's like normally distributed or close to normally distributed? And when you really kind of unpack the central limit theorem and think about why that should be, it
mm,
really is kind of this very, it's both a deep result, but I think also a beautiful result. And part of the reason why it's beautiful is it explains some of the things that we see in the natural world, like in terms of variation and what the likelihood of different variation is. It gives us some understanding of how that variation might arise, like what are the
mm,
factors that lead to it. And the fact that it also kind of enables a whole set of mathematics, like things like doing z-tests and t-tests and hypothesis testing, all this kind of
mm,
stuff, based on the fact that under particular conditions we actually get these things that are normal or close to normal, like t-distributions or
mhm,
something like that. And like a priori, like before you understand probability, like you can kind of see the world and be like, yeah, if someone told me what's the distribution of heights of people like in North America or something, and I'd be kind of a bell curve. And it's like, yeah,
mm,
but why? Why is it a bell curve? And like the central
mm.
limit theorem gives you some intuitive understanding as to why that might be the case. So I think it's beautiful of like how mathematics helps explain the real world.
But it's also so counterintuitive because I mean, and I think maybe it's worth unpacking a little bit what a normal distribution is. I think this is also just like one of the most useful concepts in life ever. The idea of a bell curve and being able to reason probabilistically around. And what the central limit theorem gives you is license to it's a reasonable default to assume things will be normally distributed. Um, and and you see it show up everywhere. You see it show up in heights. You see it show up in virtually all like natural distributions. Um, do we want to talk about the normal distribution a bit more to give people an intuitive understanding of how it comes about? Um,
Sure. So I think, in relation to the central limit theorem, right, the notion, what the central limit theorem basically says is if you add together a bunch of quantities that are independent of each other, independently generated, that sum is going to, the distribution of that sum is basically going to be this bell curve, which is a normal distribution, has a particular mathematical form that is basically sort of an
mhm,
exponential function. And it has two
mhm,
parameters. One parameter is the mean that sort of says, okay, if I have this curve, I'm trying to make a little bell curve, but I can't,
mhm, mhm,
try to do a triangle to do it justice. Where it's located on the number line is the mean, right? What's kind of that
mhm,
midpoint. And then how wide it is, like how varied the distribution is based on the variance. So it has these two
mhm,
parameters. And then those two parameters basically are, when you add a bunch of things together, you can sort of compute what those parameters would be based on the central limit theorem. But if you think about it as just the notion of a normal distribution arises from adding together a bunch of independent factors, it helps
mhm,
explain a lot of stuff. Like if you
mhm,
look at something like what's the distribution of exam scores in a class, right? Well, it's
mhm,
sort of like what is an exam made of? It's made of a bunch of independent problems. Well, not more or less. They're not actually
mhm,
entirely
mhm,
independent. It depends on the knowledge state of the learner and stuff like that. But when you amalgamate a bunch of things into some sum, you are getting something that's closer to this normal distribution. And there's all kinds of kind of technical caveats with
Hmm.
that. But
Hmm.
part of the thing is, when people think about that, they're like, well, what about the underlying distribution? Like, I can understand, like, if I roll 10 dice or something like that, and I want to say, what's the sum of the 10 dice? Well, I know all the dice rolls are independent. So if I add a bunch of them together, I'm going to get something that looks kind of like a bell curve, even though it might not be continuous in the case of dice. Um,
Hmm.
but, and the dice are equally distributed, right? They're sort of uniform distribution if they're fair dice. But the interesting thing about the central limit theorem, it says, you know what, the distribution of the
Hmm.
underlying thing that you're adding together doesn't have to be uniform. It can actually be a bunch of different shapes, modulo a few
Hmm.
caveats, a wide variety of stuff. And when you
Hmm.
sum those things together, you'll still get a normal distribution. Like, it doesn't really matter what the shape of the underlying distribution is. That's kind of mind
Like,
blowing.
it's crazy. It's crazy. Um, Okay, so what I think that sort of covers, I think what we can reasonably do justice within like 40 minutes of talking about probability. I think like it's worth maybe transitioning to some of this stuff in the real world. And one of the examples we saw in class, and I think it's like one of the examples that has affected basically everybody who is a citizen of the modern world, is spam filtering and your contributions to spam filtering and deciding whether information is relevant to a given receiver of a given message or not. So how does this all? I want to throw in the keyword just to show you that I didn't forget naive Bayes, but like, how does how does
Well
this
done.
get a yeah, how does this get applied into a very real world use case of the internet is blowing
Sure.
up, it's 1998, what do we do?
Yeah, so in the late 90s, I was fortunate to be an intern up at Microsoft, actually. So back in the day when I was still in graduate school. And this is, early days of where email's widely available, right? So it was just a couple years before then that like Hotmail got acquired by Microsoft. If you wind back several years before that, there wasn't sort of free commercially available email for everyone, right?
Hmm.
Maybe people had email through their work and it might have been limited, but this was the time in sort of the mid to late 90s where email was becoming a common consumer thing and people were getting it. And so when it becomes a common consumer thing, there's people who want to kind of send you marketing messages, right? Or make you take
Hmm.
some action or potentially involve you in some kind of scam or something like that. So the volume of spam email starts going up pretty markedly at this point. And so the problem came up, well, how do we try to filter this out? And the notion of using Bayesian methods, which were very popular at the time, they're still pretty popular, but I think these days a lot of
Hmm.
people kind of do deep learning kind of stuff, which is great too.
Hmm.
um, but was basically say, if we were to take if a message that comes in, how can we determine if it's spam or not? Well, like most machine learning problems, if we're trying to do classification, like say spam or no spam, what we need is some data, some examples of what spam looks like, and some examples of what spam is not. And we can basically say, like, well, the words might be indicative. The words that are in the message might be
Hmm.
indicative of whether or not it's spam. So let's treat the presence or absence of every particular word, right? And you could think of in like English, there's
Oh.
hundreds of thousands of words, right? And then if you even consider things that aren't words, like you're getting into millions or hundreds of millions of distinct tokens. But let's say we look at the presence or absence of these things. We can say, what's the probability of the presence of this word in a spam email versus not a spam email? And so it turns out the set of words you actually need to look at is relatively small for an individual, because
Hmm.
the things that are indicative, most words may not have a lot of information content, but there's really some words like, lotto winner or some phrases that might be much more indicative of spam than some other word like conference proceedings or some
Hmm.
phrase. And so by computing these probabilities, basically what naive Bayes does, it computes a bunch of the probabilities for each of the words appearing or not appearing and treats them independently, conditioned on whether or not this message might have been spam or not been spam. So it's a
Hmm.
mathematical simplification that would take something like the full joint probability table would be exponential in the number
Hmm.
of words, right? So it's like it would be like 2 to the 100,000 power. It's just you can't compute it.
Hmm.
But naive Bayes makes that a linear computation. It says if you have 100,000 words, you're going to do on the order of 100,000 computations, which on modern computers is very straightforward. To make a determination and compute a probability, is this thing spam or not? And then
Hmm.
depending on how bad it is to like filter out a legitimate email versus allow in a spam email.
Mm.
And those two things have different costs associated with them. You sort of figure out what's the right threshold to label this thing as spam or not.
Hmm. And it's interesting that one of the things that you said is like well, you said that like there's more of a deep learning way to do it now, which is true, but also I think it's just as Bayesian. I think deep learning is just Bayesian that does the extra effort to figure out what the dependence relationship is between between the variables that you're presenting to it. It's just it doesn't have the convenience of assuming that the any given word doesn't depend on any other given word, but also uh, sort of like following on that is that you can think of like a very sophisticated deep learning network like chat gpt or the gpt api that has a very well defined computational cost and a very high computational cost. So like and you think about the scale that you need to deploy these systems at, and sometimes the solution isn't the full on solving of the formal problem. Sometimes you need to take on the very pragmatic approach of saying like this is the trade off that I'm settling for, and this is the rate of assumptions that I'm going to make, and this is the computational cost that I'm able to incur. So I think that like as an innovation in terms of that, I think it's like another wonderful mathematical application into it is something that we all feel like. I think like we I think of kids who grow up in the TikTok era, and they the way spam looks to them is completely different. It feels like a complete intrusion to their lives, and something that how could you ever let this happen? And I think about how when I was growing up and I was getting so many requests from Nigerian princes to you know help out, um, and so what are some of the most like the highlights of your implementation of some of these concepts in industry?
Well, I mean, the fact that something like a spam filter gets rolled out to like millions of people, right, or hundreds of millions of
Hmm.
people, is really satisfying. I think that's
Hmm.
one of the things that for me provides a lot of satisfaction. Is there is a mathematical side to things, which is just kind of fun playing with math, and there are many
Hmm.
times like my wife just says like, "What are you doing?" I'm like, "I'm playing with math." Um, and so there's a satisfaction you get when like the math works out or you figure out some particular model. But I think at least for me there is even greater satisfaction when that translates into something that people actually use. And so you could take something that starts with some principles, those principles turn into like some decision making that you can have some confidence with, and then that decision making turns into an actual product or feature or whatever the case may be that impacts people's lives. So there was the spam stuff. I worked at Google for many years. Some of the stuff that I
Hmm.
worked on there was related to like better search, or there was also some stuff related to ads in terms of like how do you try to figure out what is more relevant, right? Um,
Hmm.
and so things like that are just
Hmm.
satisfying to see at scale. I
Oh
think
my
that's
gosh,
really
is this so was this some TF IDF type of stuff? I was thinking about this as you were describing some of the applications.
Yeah, so I think there's the set of stuff, and these days I'm far enough removed from it that I don't know what's the
Yeah,
full
yeah.
set of stuff that actually goes into Google's system. But there's a combination of things like textual features, right? What are the actual
Mm.
words that appear on a page? There's the link structure, obviously, like the PageRank algorithm, and what kind of information is an anchor text, stuff like that. But there was also a lot of information that you get. An appreciation for like some user interactivity information, like not
Hmm.
just does someone go to a site, but how long do they spend on the site, right? So if I go,
Hmm.
like if I do a search and the number one result I click on, but then I see in like the logs 5 seconds later the person clicked on number two, that probably means that number one, even though they clicked on it, was not actually the information they were looking for. So
Hmm.
part of the awareness and understanding was there's lots of different sources that are potentially signals of information. What something like probability theory, and if you layer on top of that information theory or a bunch of other ways that you can look at it, allows you to do is figure out what are the signals that provide most information about the decision you're trying to make, like showing something useful to a user or whether or not they found a particular search result to be relevant.
Hmm.
And so that's how I think about the math. Is really what the math is the math is in service to some goal that you're trying to achieve. I mean, there are some people who like math for the sake of math, and I think that's beautiful too. But I appreciate, like, there's some goal that I want to get to. What I would really like to have, rather than just hacking something together, is I would like to have some principled way where I understand the principles and how they fit together and how the assumptions that go into it. So I can also tell, like, are the assumptions violated? Are they not violated? Are there ways to relax the set of assumptions that we're making? And how that ultimately translates into making a decision, because
Hmm.
it gives more confidence in the entire kind of process as opposed to just the final decision.
Hmm. No, it's awesome, and I think like one of the real privileges of going to school at Stanford was getting to learn from people who had the experience of deploying these things in industry and sort of wrestling with the implications of this at tremendous global scale. And I wanted to share the story that I heard from somebody who did not use probability in figuring out how to optimize. This was also very deep in the stack. So they were trying to optimize dictionary allocations, so map allocations, and like they were trying to tweak the hash function to make it faster or something to that effect. Um, and this was so deep in the stack that this was like the language's data structure. So they were taking like class objects and like putting them into the tables and to look up tables to know which methods to access and whatnot. And eventually what they decided at some point for some performance reasons is, what, we're just going to assume that the input to these maps is going to be random, and so we're just going to say the hash function is going to be modulo the first bit or the first byte of whatever the string you input is. Um, and all of a sudden, whatever naming convention gets adopted by the company, and they're all using these very sort of like hierarchical naming conventions, and everything is getting allocated to the first bucket. And all of a sudden, their hash maps have one vector that has like billions of things in it. And it's just one of the, I think it's like the perfect example of how you should reason about probability. It's kind of a fair assumption to assume that if you're building a general purpose thing, you're going to get a uniform distribution over that space. But then you get to this very specific instance and it's quite the opposite. um, I thought I was
That's an
funny, and I
awesome
wanted to
example.
yeah, isn't that funny? And it was one of the big animation studios. I forget exactly who, but it was, they were trying to compile the whole movie, and it didn't fit it's just when theory meets practice, that's what happens. Um, okay, so I wanted to switch gears a little bit. So you at some point were in industry, and at some point you decide to commit fully to computer science education. And I was certainly a beneficiary of that change, and multiple levels. Actually, I took two of your classes. I participated in a program that you spearheaded that was about CS education, and I taught CS thanks to the initiatives that you did, that you initiated. And now you are the captain of the ship, of CS at Stanford, and you're navigating all the changes in the world and the scale of the impact that your students can have, but also the number of students that are under your purview today. Um, what was that decision of committing to CS education as the thing that you wanted to do?
It's a good question. And I think part of it is just, how I grew up. I come from a family of educators. So, like, my brother is also a professor. My wife for many years, was a high school teacher. Both of her sisters are high school teachers. One of their husbands is a teacher. My mom worked for
Mm,
our school district. My dad, after he retired from his regular job, like, worked as a aide for special education. Like, education is just something that's been very important in our family.
mm,
And, like, even when I was a kid, like, my parents always impressed on me the importance of education. I
mm,
was actually born in Iran. They moved to the United States in significant part so my brother and I could be educated here.
mhm,
So when you're making, like, big family decisions around something like that, it just has a significance to it. And so, from, I think, like, in fourth grade or something, I wrote an essay about what I wanted to do when I grew up, and it was be a teacher. And
mhm,
then I got into computer science, and I just thought, wow, this is this amazing thing. And when I got to college, in the same program that you did, it actually just started when I was an undergrad. And I got involved in teaching computer science. So it's like take these two loves, teaching
Hmm.
and computer science, and there's a way to put them together. And it turned out there's this career called being a professor that is about doing research in the domain and also worrying about education and teaching.
Hmm.
And that's what motivated me to get a PhD. And I'd say the time in industry, even though I was there for about a decade, actually, if you put together
Hmm.
all the time I was in industry between finishing the PhD and coming back here, in some sense, I mean, I loved it. It was a great thing, but
Hmm.
in some ways, it was also a diversion from my real passion, which was education. And so it was
Hmm.
kind of a homecoming to be able to come back to an educational context and just really focus on that. But I took the learnings from industry, and there were just a lot of really interesting experiences there. And when you can bring that back into the classroom, that's kind of powerful. Where you could say, like,
Hmm.
why should you care about this thing about probability? Because let's talk about how, like, Google does machine allocation, right? And
Hmm.
now suddenly this very abstract mathematical concept gets grounded into a real world thing that people would care about. So I felt
Hmm.
kind of fortunate that it was possible to make those connections.
Hmm. And what are some of the most rewarding memories of? Well, actually, even before. I mean, how many thousands of students have you taught? Do you have a counter? Do you have
I
a like a?
don't have a counter, but there were many years where, like, during a year, there was more than 1,000 students taught.
Yeah.
Um,
I was in one of those years, so I know that for a fact you taught more than 1,000 years the year that I took it. The 1,000 students. You know what I'm saying? Um, so, what are some of the rewarding stories there?
I mean, there's a lot of them, right? And they take many forms. So one of them is just something like this, right? Is being
Mm,
able to reconnect with a former student, seeing the
mm,
kind of stuff they've done. Like, you feel in your heart a little warmth to be like, wow, they remember some of the stuff from class. Maybe it was useful to them in their career. So stuff like that, it just actually, like, really has an impact. It's something that's
mhm,
motivating. And at the time, there's things that are like when a student's in a class and they're struggling with something, but then they get the
mm,
concept, right? Or when they realize, like, how the thing that they are learning is relevant to some other thing they want to do.
mm,
Um, and so that kind of satisfaction of seeing kind of possibilities open up for students, right? There are a lot of students who take like 106A, right, which is the intro programming class, say they never would have considered computer science as something they
mm,
would have done, but they took this class and it opened up new possibilities for them, and then they went and had a career in computing. That's
mm,
just there's a lot of joy from that.
mhm. And it's beautiful. I mean, like I would just want to echo that because I certainly felt the joy of the light bulb moments, and then the joy of the distributed random light bulb moments in others when they finally get something like recursion, or they finally get something like pointers, and like all of a sudden you can see the map change in their minds about how they thought the world works and how it actually works, and like there's a beautiful sense of gratitude also in the CS program that I was fortunate to be a part of, where everybody's always giving back and being very thankful for the contributions that that led them to their own learning and to the students. And well, that's awesome. What about some of the challenges? What are some of the like one of the some of the most difficult things over the past you know 10 years, 20
Yeah.
years?
I'd say the difficulties. I mean, there's always things that are not so fun to deal with. Like one of them is,
Mm.
potential plagiarism issues.
Yeah.
And it's not that students are, like, evil people or something like that. It's just they can be under a lot of stress, and sometimes they make a bad call, right? So it was like 3 a.m.
Hmm.
and their program wasn't working, and there was someone down the hall who had working code and was willing to share it. So they made a bad call. And helping students get through that process, where the idea is, like, if you can be responsible for what you did and understand the things about it that weren't right, like, I'm on your side. I want you to get
Hmm.
through the process in a way that kind of minimizes pain and maximizes understanding and learning so it doesn't happen again, right?
Hmm.
It's still not a pleasant process. And there are, honestly, some cases where students just, they, even in the face of overwhelming evidence, because it's an identity thing for them, they're just not willing to admit that they were that person or
Hmm.
that they cheated. And so, that's the place where it gets a little bit more unpleasant. The other
Hmm.
thing too is I think we face a lot of challenges around communication. I mean, we're certainly seeing it now. We're living in a time that has a lot of significant, sad world events going on.
Hmm.
And especially for people who have strong feelings, it becomes difficult to be able to maintain a kind of respectful communication engagement. And
Hmm.
I think that's the thing is like really what we want. I mean, part of the reason why we have difficulty in the world is we have people who don't try to understand each other, who don't try to remain respectful and see what different viewpoints are, even if they don't agree with them, to understand where they might be coming from, and to engage in a process that says, let's try to create greater learning and understanding so we can get to a place where we're all better off rather than ignoring other people or denigrating them or whatever the case may be. And we just see kind of more challenges of that in all spaces, but certainly in the educational one.
Hmm. What about in terms of the sort of thinking program wise? In terms of, so when I was there about 10 years ago, CS had just become the number one major. And I guess I don't know if it had just become, or it was a recent event in recent memory, that computer science had become the most popular major at Stanford, and that lead has sort of just steadily grown. And like a significant fraction, I believe, almost almost 30% of Stanford students end up declaring computer science. So how does the teaching infrastructure expand to sustain the level of quality that you had when it was a third of that size?
Yeah, that's a good question. And part of it is there's just a real deep departmental commitment to education.
Mm.
So, in the computer science department, we have a very vibrant and large compared to other departments staff of lecturers who are focused on just really high quality teaching. And if I might kind of get a little brag in there, I think the education team. I'm not including myself in this, but I think our team of lecturers as educators are just world class. I think we really
Hmm.
have, if you think of it in aggregate, the best group of computer science teachers in the world. And they're people
Hmm.
who really care about learning. They care about their students. They put a lot of time into it that you don't necessarily see. Like people often like go into a lecture and they're like, wow, that was effortless. And it's like, no, there was 40 hours of work that went into making that 1 hour of lecture seem effortless and to make it so that the majority of students in the class could really understand what was going on. And when you see that kind of commitment, it's pretty astounding. Like it pushes you, like seeing the commitment from my colleagues and how hard they work at the endeavor of education makes me
Hmm.
work harder at the endeavor of education. And I learn from them, right? And I hope I could maybe have something to offer in return for them to learn as well. But it's a challenge. Like,
Hmm.
a few years back, right around the time actually when we became the largest major, I think it was right around the time you were a student, we had a faculty retreat where we were looking at all the numbers going way up. And we said, a lot of other schools are limiting enrollment in computer science, right? Limiting the number of majors, limiting enrollment in classes. That's one way we could deal with this problem. But we need to understand that if we do that, it's going to have uh, distributional effects. There will be some people, for example, who
Mm.
exposure to computing in high school who won't be able to come in and compete at the same level with people who have a bunch of experience. And then if we limit enrollment based on something like GPA in the intro classes, which is what a lot of other schools do, we disadvantage students who didn't get computer science at their high school, right? They're going to just
Hmm.
continuously be disadvantaged. And so then, and much to warm the cockles of my heart, it was unanimous among all the faculty that
Hmm.
we would not limit access to the major. We would not cap enrollment in classes whenever possible, right? There are some classes where it's like, oh, it's a
Yeah.
robotic class. We only have 20 robots, right? We can only have a certain number of students. But other than that, like the major is uncapped. And so
Hmm.
there's a lot of people who want to do computer science. And the message is like, if you get into Stanford and you want to do computer science, once you're here, you can do computer science.
Hmm.
And so we have at this point, I think last year we had over 500 students declare computer
Hmm.
science, and a class of incoming students at Stanford is about 1,750.
Yeah.
Right, so you can do the math, and it's pretty significant. Right? We have like over 50 majors at Stanford. So if they
Hmm.
were uniformly distributed, you'd figure there's about 2% of students in every major. The fact that
Hmm.
we have like you know, approaching 30%.
Mm.
We're not like 150 time or 150% of like the average size or 200% the average size. We are more than 1,000% of the average size.
Hmm.
And that creates some challenges, but we try to do the best we can.
Hmm. Yeah, including deploying undergrads who have just been through the process to then, like get some a chain reaction of knowledge and allow them to. And I will say, I don't think I've ever said this before, but like section leading was not just an incredibly rewarding experience for me in like having to master the material and then convey it, but it was also like the best source of income as a college student. I felt like I was like, oh my gosh, like this is a job, sure, but like and it was like the first thing that I did in the U.S. where I was like actually making money, and it was pretty good pay at the time, I will say. Uh, so as an undergrad, so I thought of it as not just giving opportunity to master the material, but also just like a really like financial opportunity too, which I remember now very distinctly enjoying. What about so there's the quantitative approach, the scale of the just the number of people that you have to push through the pipeline. But there's also, I think, software is eating the world, and like more and more things are software defined, and more of human interactions are mediated through software than ever before. So, do you also spend some time thinking about the impact that the software that the students write um, has an impact layer to it? Do you think about it that way?
Yeah, absolutely. And recently being sort of the last 5 6 years, I've been collaborating with two colleagues, Rob Reich and Jeremy Weinstein, who are in the political science
Mm.
department. But Rob is a moral philosopher, basically, and
Hmm.
Jeremy's a public policy person. And one of the things we do is we came together to teach a class about basically ethics, public policy, and technological change. So thinking
Hmm.
about how what people build in software or in technology impacts people's lives in different ways. How do we think about that impact in terms of value trade offs that might exist? And then what happens with respect to when there are certain values or particular kinds of norms that we want to uphold? That's where public policy comes in. And that's why all these
Hmm.
things kind of come together. And ultimately, what we want students to really think about is when they develop technologies, who is being impacted by those technologies, in what ways are they being impacted by those technologies, and who has power, right? Who gets
Hmm.
to make the decisions? So you could think about something like an end-to-end encryption system, right? So we could think of,
Sure.
okay, now there's a value tension there, right? The reason why you might have end-to-end
Yeah.
encryption is you care about privacy a lot, right? And so
Hmm.
you could say, yeah, I'm a privacy absolutist. We should have total privacy. Everything should be end-to-end encrypted. And you say, okay, that's one viewpoint. But you need to understand that if you want to do that, total privacy also means total privacy for people like human traffickers and child
Hmm.
pornographers and terrorists. Are you
Hmm.
willing to accept that as part of the price of total privacy? The answer
Hmm.
might still be yes, right? We're not making a
Hmm.
value judgment about the answer, but what we want you to think about is what that value judgment is and then
Hmm.
how it translates into technology, right? So you could also say, well, yeah, maybe I don't want privacy in those cases, but the technological solution to like create a backdoor creates too much insecurity, so it's not worth it. Now you
Hmm.
begin to unpack the pieces. You begin to peel the onion and get into more and more details around what's possible technologically, what we might want from values, how we might want to codify some of that into policy, right? The machine learning stuff, you see this all over the place with things like, is there bias? Is there unfairness in the deployments of machine learning algorithms in terms of who's impacted by their decisions? And those are questions
Hmm.
like, what data do you have? What kind of biased decision making may have been made before that impacted the data that you're training on? Are you even auditing the algorithm, right? Are you running tests to try to determine if there is bias or not? And so some of the, many of these things are not about like evil people. They're just about having a level of awareness that these are things that need to be measured, mitigated, corrected when possible, as part of the decision making process to deploy software.
No, that's fascinating, and I took a class where Rob Reich was a guest lecturer, and I think it was exactly about incommensurate values and how like there are some things that we just can't pit against each other, but we still have to think them through. So I remember, getting a great sort of like light bulb moment there too. What about thinking 10 years out, which I know is like impossible, given the, LLMs, given ubiquitous, smartphones and ever more sort of, immediate HCI interfaces. How do you think about computer science education in a world where AI and perceptive tools have a more profound role?
Yeah, I think there's a lot of promise, and like with that comes peril, right? And so
Hmm.
the promise are things like, AI uh, has an ability to provide a powerful technology to a lot of people that can be used in different ways. So, for example, you could have automated tutoring tools, or you could have
Mm.
tools that help provide more personalized educational experiences for students. That would be lovely to see, and if it were widely distributed, that would be great. It's not going to completely level the educational
Hmm.
landscape, but it might be able to help at least address some of the gaps, especially in places where it might be more difficult to have a large number of high quality teachers for whatever reason, right? And
Hmm.
so if there's ways that technology can help address that, that would be great. But at the same time, to do that, that's a human decision. We need to be mindful of that because it's also
Hmm.
possible that says, hey, you know what? Technology provides these great advances like personalized education. And the people who get access to that are the people who already have access to a bunch of resources. They're rich school districts that can afford the computers, or they are, rich families that can afford access to this stuff. And it has the potential to exacerbate the gap that actually
Hmm.
exists. And so when you see that, it just requires being deliberate about decision making to say, we understand that there's now this accelerant, right? I think that's really what AI provides is an accelerant for a lot of things.
Hmm.
What is the outcome we want? We have to plan for that outcome because we're going to move at a faster rate toward getting there. And so we need to do the right things by it. How do we allocate resources to make this viable and to make it happen? That's the place where it could go either way because this is the
Hmm.
place we're making those decisions now.
Yeah, I think it's like one of the reasons I decided to embark on this particular project is I think that the level of empowerment of the average person is going up because of access to these technologies, and figuring out a common language to reason around our issues and situations is sort of a step forward in the right direction to help more people be involved in the conversation about these discussions that are happening and that will affect everybody's lives. And as you said, they're accelerating at a dizzying pace. Um, and okay, so I have one final question. It's kind of a trivia fun question. That does music count as playing with math?
Wow. Wow. Um, yes and no. So it's too tough to answer one way, right? 'Cause it's how far you want to push it, right? It's like at
Hmm.
one level, there's a lot of mathematical beauty in music, right? Like timing,
Hmm.
how notes fit together, how things sound together. Back in Bach's day, one of the things that they would actually
Hmm.
do is they would write these symphonies and leave out particular notes as a puzzle. And the idea was that the note actually is uniquely determined, right? You need to figure out what it is
Hmm.
and fill it in, but for it to sound right, for it to have the right, progression, and so they would, and because there's a mathematics to it, right? But at the
Hmm.
same time, there's just this beautiful I mean, you're obviously a guitar player, right? So I would imagine there's
Hmm.
times you pick up the guitar and you play. And when you're doing that, you're not worried about the particular timing, or you're just trying stuff out that maybe even when you start playing it, like sounds kind of discordant or whatever. And then you're like, oh,
Hmm.
maybe I could do it this different way, or I could put stuff together in this other way. And so there's this creative process where you're not so much maybe consciously thinking about the math, although like the things like the timing and stuff are still impacting you. So I think music is one of those things that I think is a beautiful combination of I would sort of say your creative mind and your rational mind. It just
Hmm.
comes together. And personally, I just love music. So
It's so hard not to love it. I mean, how could you not love it? No, that's awesome. I wanted to hear your thoughts because I've only recently begun to more intentionally connect music and math, and the more you look, the more um, I've found it as a really powerful way to connect with math. Where I feel like I struggled with math, like it was a hard thing that like in my mind was like a difficult thing that only smart people did. Whereas, like reframing it through music has been like, no, wait a minute, math is something that everybody does and everybody enjoys. They just do it in the form of music. Everybody enjoys hearing harmony. Everybody enjoys hearing a beautiful melody. And what is it about those that, what is it about the properties that are exhibited in those features that make it, beautiful? And then you can get into the whole philosophy of beauty and stuff, which is beyond the scope of our conversation, unfortunately, but perhaps for a future episode, maybe. Um, Mehran, this was awesome. I really appreciate your time. It really means the world. I hope you have an amazing rest of the week.
Thanks. I really appreciate it. I really appreciate the chance to just be able to chat with you and to go through such a myriad of topics. It's just lovely. So thank you so much.
You got it. I'll send you a link as soon as it's done.
All right. Wonderful. Thanks a lot.